Okay, let's do a quick example where we calculate the potential of a charged rod with charge density lambda. Okay, so I'm going to go ahead and start just by drawing our charged rod. Okay, we're going to draw something like this. And for this particular problem, we're going to evaluate the potential at a point over here, P. Okay, and I'm going to define an axis that goes through the middle of the rod here, and we'll do another one here. I'll call this X. Okay, and I'll call this Z. And for this particular problem, the rod is going to extend from L to negative L. Okay. At this point P, because it's near the end of the rod, the field won't have nice symmetry. Basically, it will be hard to pick a Gaussian surface that would make this easy to solve. Gauss's law always works, but it's only nice to use when you can pick a reasonable Gaussian surface. Okay, so in this case, we've got no friendly Gaussian surface. So let's try calculating the potential instead. That's what we just learned to do. Okay, so the first thing I want to do, right, is what I've already done. I want to draw a picture and go ahead and define a coordinate system. If you find that when you're setting up your integral, it seems too hard, it may be because you didn't pick a very nice coordinate system. In this case, it's nice to have the rod aligned with one of our axes, because then we can just integrate in one direction, the z direction, rather than trying to integrate right off to some angle here. It would have been fine to put it along the x-axis as well. Okay, it doesn't really matter. All right, in this case, we are given a linear charge density. So that basically tells us we need a line integral. Okay, so we are going to use this version of our integral that allows us to calculate the potential from our charged object. Okay. Okay, so I just might write that down first, just so I can kind of get an idea about what I'm doing. And now I want to use the picture that I drew to determine what to replace dl and our separation vector with, so I can actually do the integral. Okay, so let's go over here and look at the picture. I'm going to just pick a characteristic little chunk of our line that I'm going to call the dq. This is our little bit of charge, right, that we're going to try to understand the field from. And I can draw the separation vector. It's going to point from that little chunk of charge to our point P. Let's go ahead and draw that. That's our separation vector. Okay, and then I can stare at the picture for a little bit to figure out what I need to do. Here, hopefully I can see that I'm going to want to end up integrating. If I want to integrate over a bunch of little chunks of this particular rod, then I'm going to end up doing an integral over z. Okay, so my dl prime can be replaced with a dz prime, because that's the actual direction I'm going to do this line integral. And the limits will go from L to negative L. Okay, and then my separation vector, or the magnitude of the separation vector, which you guys remember is equal to our r position vector minus r prime position vector. Okay, If I look here, this is a point that is at x. I'm going to assume that y is equal to 0 and z, okay, because it's flat on the plane here, so I don't have any y coordinate. Over here, the position of my little chunk of charge, I'll do that in red, is 0 in the x direction, also 0 in the y direction, and in the z direction, it's at z prime. Okay, so my magnitude of the separation vector is going to end up being x minus 0 squared plus, right, 0 minus 0, that would be the y, pretty boring, plus z minus z prime. Okay, and all that will be to the 1/2. I can simplify that a little bit. I'll get x squared plus z minus z prime squared, all of that to the 1/2. Okay, so I'm going to use that to rewrite my integral with that good stuff in it. Yeah, I'm going to rewrite my integral. And so I end up getting that the potential now is 1 over 4 pi epsilon naught, and I'm going to integrate it from L to negative L, and I end up getting lambda, which in this case I'm going to assume is uniform, but lambda really could be a function of z. If it's not uniform up and down the rod, I could still potentially do this integral, especially if I'm going to use Mathematica. Okay, and I get x squared plus z minus z prime squared to the 1/2. Okay, and just remember, we're only integrating over the primed z because that defines where the charge, our dq, okay, is. So we actually, this point right here, this z is more like a constant. I could have put that anywhere. It's interesting, right? Because our potential does change at different z's. But when I'm actually doing the integral here, I'm trying to integrate along the rod, okay? So I don't need to worry about our z coordinate of our position when I am doing that, okay? So at this point, I could either look it up, okay? I could look up integral in an integral table, or I could use Mathematica. Okay, so in my opinion, setting up these integrals is still fun, and it's easy. Okay, not necessarily easy, but it is easier. Okay, there's another example of doing this over a sphere. So that's in the book. I'll have you guys examine that. And now if you want, hold on, I will actually open Mathematica and we can plug this integral in. This is nice for you guys that still maybe need a little bit of more practice with using Mathematica.